So, last time we concluded with some review of modules, and we quickly talked about tensor product of modules over commutative rings with Unity. Today we'll talk about direct limits, which you tell me something you already know, you already seen. So I think that's a good excuse to skip all the proofs. But I still want to review everything. And we will begin with the definition of a partially ordered set. So we have a set and we have an ordering is a set I with a relation is less or equal such that everything is less or equal than itself. And we say less or equal, but of course it doesn't mean less or equal. Then we have transitivity. Sorry, not transitivity, but reflexivity. So if I is less than j and j is less than I, then I is equal j. And then we have transitivity. So if I is less than j and j is less than k, then I is less than k. And okay, so this is different from an ordered set, from a totally ordered set, because we don't, because if in a totally ordered set for any two elements, you always have their one is less or equal than the other. Well, here we don't require that. And furthermore, this is probably something you've never seen. Such set is called directed or filtered. Filtered, directed. If every time you have two elements, there exists a third element such that I is less or equal than k and j less or equal than k. Okay, so so saying a totally ordered set, if you have I and j, then either I is less or equal than j, I is less or equal, or j is less or equal than I. But here we have something different. It's just if you have two elements, there is always someone which is greater than both. Okay. And an example, which is really the reason why we introduced the whole thing, is open sets in a topological space with contained. Yeah? So, but not in the sense that, so what it means is that U is less or equal than V if and only if V is contained in U. So kind of reversed. So this is a contained, this is a less or equal. Okay, because here you can simply take this K, this filtered part, to just be the intersection of the set corresponding to I and corresponding to J. Okay. And now that we know what is a directed partially ordered set, we can define a directed system of our modules is a family of our modules. And the interesting thing is that they're indexed over a directed set. And we have basically transition maps. So in such that if you have two indices and one is less than the other, then there exists a morphism of our modules from AI to AJ with a couple of properties which should fit here, yes. FII is the identity. And if I is less or equal than j, less or equal than k, then fik is just a composition of fjk composed fij. Okay. So just observe this. The order of the indices is different than the one we use for transition maps. Yeah? Transition maps, the domain is the one on the right and the codomain is on the left. Well, here is the opposite. Okay. And why do we introduce all of this? Well, because the theoretic sets, in particular theoretic systems, are the one that let us speak about limits, direct limits. So we take a dialectic system. Of our modules, and remember, R here is always, so we use the same convention we said last time. R is always commutative ring with unity. Then there exists an object, which we call the direct limit of this AJ, and it's an R module. So there exists this and maps Fj from AJ into this R module such that Fi is the same as Fj composed Fij when I is equal to j, and such that we have some universal property for any R module B and any family of morphisms Gi from AI into B, which also satisfy this property. So Gi is Gj composed Fij for I less or equal than j. Then there exists a G which factors this map. So it is a morphism such that Gi is nothing but the composition G composed Fi for every I. And furthermore, and this is clear by this universal property, this pair of the object together with these maps is unique up to isomorphism. So as you said, you're comfortable with this object, we'll skip the proof. But I do want to, so no proof. But we look at the categorical viewpoint. The categorical viewpoint. So what do I mean by this? So how do I see it? So when I say categorical viewpoint, what I mean is that I want to draw diagrams, basically. And so what is a directed system? Well, the way I imagine it, especially when it's filtered, it's basically a reverse tree. So you have your A1, maybe your A2, your A3, and then this goes to, I don't know, to A4. So this would be F14, no? And maybe here you have A5, and here you have F25, and here you have F35, and then maybe, you know, goes to A6, and this goes here, but it also goes here. You know, you just have some in this maybe goes, I mean, maybe this set is finite, this set I is finite, maybe it's infinite. We usually want it infinite. Yeah. And the way I want to think of this is just one object, the object diagram, let's say. Yeah. And what do we have? So here is saying that every time we take another module B, so B, and you take these maps, GIs from, you know, so you have G1, you have G6, you have G4, and you have all the other ones, of course. Yeah. So it's saying, okay, if you have this, I want to think of this purple one, not as like a lot of maps, G1s, like G1 goes from A1 to B and G4 goes from A4 to B. I kind of want to think of it, no, I want to think about it as like one map from, or one arrow from the diagram, from the old diagram to the object B. Okay. And what this proposition is telling you is that every time you have this kind of drawing, somewhere here in the middle, you can put a new object, which is this direct limit of AJs, which factors everything. Yeah. So this direct limit is somewhat, I mean, it's, well, it says is the object which factors maps from this diagram to other R modules. Okay. And let's look at some examples of how this works. For instance, let's look at the direct sum. So I take I to be just n, but with trivial ordering. So I is less or equal than I, but that's it. And no more. So we don't think n as the standard ordering. You just say that everything is less or equal than itself, and that's it. So this is not directed with this ordering, yeah. But we actually it is directed. Why is it not directed? Right? I mean, it satisfies clearly all of this, and it also satisfies this because you just take I itself. So yeah, sorry.
No, I think it's not directed because we need to choose a k that's
Different than I
that
and J, yeah.
yeah. And if we have 1 and 2, then we have a problem because
Oh yeah, sorry for every,
only
yeah, sorry, yeah, of course, of
k
course, of
would
course. Yeah, sorry. So this is not directed, yeah. But we can consider still this limit. So in general, you need this direct set, but in this case, things work because they're so simple. So what is our diagram here? Our diagram, you simply have this A1, A2, A3, and there's no arrows between them. It's just all of them. And each of them then has a map to this limit. So maybe I should do this. And here we have our B. And this is factoring these maps. And the claim here is that this limit is nothing but the direct sum of these objects. And the Fi's goes from AI to the sum. And you simply take an element A and you send it to the infinituple, which is all zeros but the A. So I'm going to write it like this. Sorry. Yeah, so this means that it's basically always 0, because this is 0 if I is different than j. But if I is equal than j, then we put a. So it's simply like, how would you imagine the embedding of one factor into the sum, no? Just a complicated way to write it. And okay, let's see, does it factor? So what are these maps? So if you have the gj from aj to b, then our map g, for every gj set, we have to find one map g, that needs to go from this direct limit, which we hope is the direct limit, to b. And we simply take aj, so we have this sequence, and we send it to the sum. Okay. It satisfies the factoring thing, because here you're simply sending ai into itself, and when you take the sum, you only get gi, right? And otherwise, this is well defined because this is always a finite sum. Because this is the sum, not the product. So only finitely many or non-zero. Okay, so this is our first example. Very easy. What am I going to say here? Okay. So just an observation. If I have a directed system, Ji be a directed system of our modules, and we take T to be this direct sum, so you kind of forget all the old arrows that are here in the directed system. And we consider the natural projection. So what I mean by natural projection, well, basically you send an element here into the corresponding one on the what's it called, on the diagram, and then from the diagram you go to the limit. Okay. Then for each a in this limit, there exists an element here which represents that limit. Okay. This maybe is not so intuitive, right? Because here I'm saying that this maps pi goes from the sum to the limit. But here I'm telling you that there is one element in one specific module. So in principle, we should have, so I kind of have to justify this. The day is pi of a string, of a finite string, but a string nonetheless. So I'm thinking this as an element of the sum. Yeah, finally many of them. For a j I in a j I. But the thing is, since I is directed, there is a k which is greater than all of this. Okay. I mean, it works pairwise, so it works for any finite number, no? So when you're taking pi of a j1, comma, 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 a jn, is the same as taking pi of the sum of f j I k a j I. So we're like going into K first, into AK first. Okay. And now this is an element in AK, which is this one, yeah? This AJ that we were talking about before. So similarly, we can show that if we have multiple elements in the limit, there exists 1j and elements in this AJ such that Fj of AK is alpha K. So here we're just saying that if you have one element, right, in the limit, then this can be represented by only one ring, basically. And here we're saying that even if we have multiple ones, we can always assume that we're just in one ring. No? I want to talk about direct limits of rings now. In particular, and the interesting thing is that a commutative, that R, our commutative ring, is also Z module. Because every commutative group is a Z module. And so we can take the direct limits of such objects. So Rj and rho ij be a directed system of commutative rings. Commutative rings with unity, such that this rho ij are morphisms. Then the direct limit is a commutative ring because it's also Z module. The ring with this maps rho i's morphisms. Okay. So this is I call it corollary because this is actually adding a little thing, is that this limit, it's also commutative. Yeah, this is not part of the preposition. They were just saying that the direct limit of modules, it's a module. But here we're adding that this is commutative. Yeah. But this is very easy. So I just need to prove our commutative. This is very easy by what we said before. If we take two elements, then there exists just one j in the index list, and Rj, Sj in Rj, which represent these objects. Yeah. But then we can define R time S as simply the image of Rj, Sj. And since this is commutative, now this is commutative. Okay. And everything is respected because this Rj is a morphism of modules, and everything works. Okay, so now what I want to do is basically, so normally we were saying before that we're talking about morphisms of R modules. sorry, direct limits of our modules, no? And but now we see that even rings we can take the limits of rings. So what I want to do is take instead of taking the limit of R modules, I want to take the limit of Rj modules. So we take the limit simultaneously in the module and in the ring. So let's be more precise. So I take a directed system of the modules such that each Rj is a commutative ring. Yeah. And a directed system of Rj modules. So we define a directed system of R modules. So this is a directed system of Z modules, Aj, Fij, such that each one of this is a Rj module. And the Z module structure on Aj is induced by Rj. Yeah, so Rj is a Z module. And so basically what I'm saying is that if you multiply an element of Aj by a natural number, is the same as you were thinking this natural number in Rj. Okay. And Fij from Ai to a J is such that if you use this, if you multiply by an element here, so normally if we were talking about R modules, you wouldn't have this I, and you could simply bring the R outside, right? So now I want to do the same, but what I have to do is put this Ri module morphisms between. So this is for E less or equal than J. Okay. So we're basically saying that, yeah, as the modules go down these directed systems, also the corresponding rings go down these directed systems. And basically we're using Z as a support for all the structure. This is like our fixed element. So you can think that all of these are just Z modules, then you're taking a limit there, but then you also have the strings and you want things to be somewhat compatible. Okay. And the interesting thing here is the following proposition, which says that if you have such a directed system, the directed system of Rj modules, then the limit it's a module over the limit. Yeah, this is the interesting part. Okay. So now we have these new objects, which are these directed systems of Ri modules. And usually when we have objects, we always like to have morphisms between them. So let's define those. So, okay, we have two directed system of Ri models. So here we have the same module. So what is this? Well, first of all, we have that at each level, we have a morphism of modules with the corresponding ring. Yeah. And then of course you want some commutativity condition. So if you apply the morphism and then you go down, is the same as first going down and then applying the morphism. Okay, so very natural. So this should look somehow like morphism of complexes, for instance, if you think that your directed system is just straight line. And but there also the ring is fixed. It's just complex numbers in that case. So this is quite more general. Okay, note, so here we have something pretty nice, is that if you have such a morphism, of Ri modules, then it goes down. So the R modules are Aj, Fij, and Bj, Gij. Then it goes down to the limit. Yeah. And furthermore, you do have some compatibility again. Oh, sorry, not composed, equal. So remember, these Fi and Gis are the maps from the corresponding AI. So Fi is from AI to the limit, and Gi is from Bi to the limit. Yeah. And the thing is, if you apply the map before or after, it's the same. And we have a furthermore. If phi is injective or surjective for all I, then the limit is also injective or surjective. Okay. So I kind of promised that we're not going to look at proofs. But I mean, at this point, I believe that you've never seen this. This is very specific to sheaves. So if you've never seen sheaves, this is the exact thing you've seen. Yeah. So we'll go on with the proof. Okay. So we take an element here, and from our previous observation, there exists one step that represents this. And well, there's nothing better than to define phi of A as Gi plus phi of AI. Yeah, you simply kind of go up, down, up, right, and down. Yeah? And we'll not prove that this is well defined. Size. Verify it is well defined. So if I take a different representative, if I take a different I, you get the same image. Yeah? And of course, to do that, you just have to use various commutativity of diagrams. And now for the interesting part, which is to prove that if the phi's are injective, then the final map is injective, defined this way. So let's take A such that phi of A is equal to 0. So proving the injectivity is the same as proving that the kernel is trivial. These are morphisms of our modules, particular of abelian groups. Again, we can take a representative. And the fact that phi of A is 0 is telling us that GA of phi A AI is 0. And this is an element of B, right? So this is an element of B. In particular, there exists a J, which represents this element. Yeah. And this element is 0. Take 0. Nope. Okay. So we're simply, again, looking at this equality, but on Bj. But now you know that there is a commutativity relationship between those, because phi is a morphism of our modules. In fact, Gij composed phi is phi composed Fij. Yeah. But phi is injective. Implies that Fij, so if you apply AI to this, you get 0. So simply Fij of AI is 0. Okay. Our goal was to prove that A was equal to 0, and we're almost there because A is Fi of AI by definition. I mean, not by definition, but almost. But what we said at the beginning. But here I can just change this to become Fj of Fij of AI. And now this is equal to 0. So we're done. Okay. It's just some diagram chasing, which I'm kind of hiding in just the fact that I see some things commute. Okay. And surjectivity. Okay, we take surjectivity. Take B in B. Then we take a representative. So GI of BI equal B. Yeah, but since phi is surjective, we can hit this, right? So there exists an AI in AI such that phi of AI is BI. Yeah. And now we simply take A to be, well, just the image of this AI. So take A equal Fi, sorry, equal FAI. And then simply phi of A is phi of Fi AI. But we know that these two have some relationship. This is Ji phi I of AI. But phi of AI, we took it such that its image was Bi. So this is Gi of Bi, but this is nothing but B. So this one is easier. No? So the nice thing is that this morphism of of directic systems, let's say, of Ri modules, so directic system of Ri modules kind of behave well under this direct limit. And now I want to just give some properties again of this direct limit with respect to other known operations. So how does the limit behave under direct sum, under tensor product, and under our home functor. Okay. So let's say that AJ phi ij is a directed system of R modules. So not Ri modules, so just R modules. And let's take A, an R module. So here I'm not saying that A is the limit. Yeah, just a name, just another one. And the interesting thing is that hom over R, and that's why I cannot really take Ri modules here, because to talk about homomorphism, I need to kind of stick to one ring. And here I take Fij compose, if you remember what it means, no? You know that if you have a map from AI to Ij, the corresponding map after you apply the homomorphism is just pre-composing. No, sorry, post-composing. And the thing is that this is also a direct system. Directed system of R modules. But careful, this other one. So if you switch and you pre-compose, is not. This is not a directed system, and the reason is that because the arrows get reversed, so things don't work. In fact, this is what we call a inverse system.
Oh, yeah. Okay.
Huh?
That was my question. So
Yeah, basically, instead of taking the direct limit, you have to take this inverse limit,
Mhm.
which, okay, we don't know what it is in principle, but yeah, you actually know what it is. And also another thing, let's say that instead of like fixing A, you want to take an index also here. So you take AJ, Fij, and BJ, Gij, directed systems of Ri modules. So now we vary the ring as well. Then Rj, Aj, Bj, this is also not a direct system. And the reason for this is that we don't have the morphisms between them. So there is no like good maps to go from the I level to the J level or J. Yeah, there's really no good way to do this. Okay. Okay, so let's go back to the only one that is finally our module. You're like, well, okay, at least maybe here things work well. So we now show that if we take the direct limit of this, which we know now it's a direct system, is not the limit, the direct, the direct system of the limit. So nothing works there. That's what we're saying. So let's see why. So we take pol less or equal n c C module So just vector space, basically. You know, modulo wherever field is just a vector space of polynomials of degree less than n, less or equal than n, and define Fij of a polynomial to be simply that polynomial. Yeah. Then the direct limit, here it's simply the set of all polynomials. So the limit is in n. Yeah. Right? But as we've seen before, homomorphisms don't work well with polynomials. Remember, we also had this problem when we were talking about the left exactness of the hom functor. So, okay, we have this, which is this. But this is clearly not the same as the limit of homomorphism. For instance, because the identity is not here. Yeah, at no stage here you can have the identity map, simply because here you have less or equal than you must be less or equal than n. So in the direct limit you don't have the identity. While here, of course, you have the identity because it's the same ring. No, so this is like much less. It's much smaller. Okay. What time is it? Okay, we have time to finish this part. And okay, so now let's move to the tensor product. So okay, hom functor, nothing works. I mean, something works. If you have a directed system, then this is a directed system. That's it. Nothing else is a directed system, and this is not even continuous with respect to the direct limit. Tensor product is nice. Tensor product works really well. So we take two directed systems of Ri modules. So we're moving the module as well. Then both the sum with the map is just the sum of the maps. So we basically act independently on the two factors, and the tensor product. Tensor product over the correct J, over the correct ring. And here we take the tensor map. Are directed systems of our modules. Okay. And proposition, these are also very nice with respect to the limit. So both the sum and the tensor product. where of course A is the limit of AJ, B is the limit BJ, and R is the limit of RJ. RJ. Okay. So tensor product and sum work very nicely with this. And I think that the proof is interesting. So this will be the last thing for today. So proof. Exercise. Not all of it, just the sum. So prove this for the sum is an exercise, but for the tensor product, we'll do it properly. Okay. So we take h to be this limit, which in principle, we don't know that this is what we want it to be. So we just give it a name, h, so I don't have to write this thing all the time. And then the map fj tensor gj goes from aj bj into the tensor product. Satisfies. So this is well defined because simply, we're just taking the A is the limit, B is the limit, R is the limit, and the limits comes with these maps, Fj and Gj, and I just take the tensor product of them. And of course, what I imagine is that this Fj tensor Gj is gonna be the map that comes with this limit, right? But the point is we don't know that and we have to show it. And what they do is this satisfy Fj tensor Gj composed Fij tensor Gij. This do satisfy that this is Fi tensor Gi. Yeah. So in particular, you can think of this maps here as a map from this directed system, right? In particular, they induce a map from the limit by the universe property. There exists a map H from H into a tensor B, yeah, which is basically the one given by this. Okay, it factors this map. And the idea, we want to construct an inverse. Construct an inverse. So we take theta I to be simply the map from the sum into a tensor product. So standard bilinear linear map satisfying theta j of Fij plus Gij. It's equal to Fij tensor Gij theta I. Yeah, here you have the sum and here you have the tensor product. Okay. And now again, we have, this is a map from this, thanks to this is a map from this directed system. So you can think of this as a directed system to this directed system. Okay. So in particular, you can say that this map goes to, if you take the limits, here you get the limit of the sum, which by the exercise is the sum of the limits, into the limit of this, which is just h. And okay, we say that this is a plus b. into H, and this is bilinear. Okay. Because this original maps here, this theta I are bilinear. Okay. And okay, now since the nice thing is now since it's bilinear, so theta induces theta tilde from, since it's a bilinear map from A plus B, well, this is then becomes a bilinear map from A tensor B. Sorry, a linear map. What's it called? Morphism. So morphism of R modules. Yeah. Exercise. Prove that this is the inverse. So prove that H composed theta tilde is the same as theta tilde compose H, and they're the identity. I mean, of course, they're not the same because they have different domains, right? But they're both the identity. That's what I mean on the respective domain. Okay. So again, here it's a bit of diagram tracing using universal properties, using properties of limits. Understand maybe it's not very convincing. You know, this line I wrote it and like, oh yeah, probably. And then I wrote this line, you're like, oh, I don't know if this is actually true. And so that's perfectly understandable. And you're like, oh, here I have a bilinear. So it's like here I have bilinear maps between these two objects, and this should induce a bilinear map between the limits. We've never really seen this, but I promise I don't know if this is true. And I understand it skipped many details in this proof, but again, it was mostly to know this is like we need to know that this is true. So don't think maybe as an idea. Don't think of this as a proof. Think of more like a sketch of proof. And if you want to fill the details, of course, feel free to do that.
Yeah. One thing I was a little bit worried about, did we do anything to show that, like you can do the tensor product with respect to the maps between the tensor products with different rings along different rings. Do you know what I'm talking about? Like I think it's one page prior.
This Fij is Gij. Oh.
Yeah.
But this is how we defined. Remember when we had so we have a directed system of Ri modules.
Hmm?
You know, when you go from AI to AJ.
Yeah.
So this was when we defined that. Here maybe no. Fine. Yeah, there it is. Yeah, we ask this condition here, that when you bring out this Ri, you have to apply this morphism. And what is this morphism? Is the ones that tells you that this RJs, this is also directed system. That's the tricky part.
Yes. And so okay, yeah, go ahead.
Yeah, and then you're like, okay, what happens when I take this tensor product? You simply so this is bilinear. So when you take R or S on one side, when you bring him out, this comes with the corresponding row ij. Yeah.
Yeah, that's something in a new ring. Okay, yeah.
Yeah, so I mean, maybe the thing that you want to convince yourself is like, okay, we have these objects here, but what is with these maps? But maybe do you want to convince yourself that this is in fact directed system of Ri modules? Yeah, this is maybe the question.
Yes, yes, that's my
this
question.
makes sense basically.
Indeed, yeah.
That this is a directed system of Ri modules.
Mm-hmm.
Oops. Yeah.
Oh yeah.
And this one I think is clear. This one on the left is more clear. It's easier. It's just the sum. Everything is nice.
Yeah, that's okay.
This is maybe a bit more. Ooh, I'm not sure.
But
But it
yeah,
works.
with the Rhur, I think it's better.
Mhm.
No, okay, great.
Okay, so this is it for today, and this is also it for the review about this whole commutative algebra. And next time we're gonna apply all these things to sheaves, which we don't know what they are, but we'll find out.